Okay, here's another reason why we use um, probability. Okay, and again, this is probabilistic algorithms. These are algorithms that are going to work most of the time. Okay, so here is a problem that's very practical. It's used in computer security all the time. You know, when you try to build a certificate or when you ask for public and private keys in a computer algorithm, chances are that it's going to have to come up with a random large prime. Okay, and large maybe 1,000 bits. You know, 1024 bits. Maybe bigger. You know, we usually talk about that the length of the key. So this security has 512-bit keys or 1024-bit keys, right? And we need to find a large prime. So how do we do that? Okay, so here's the solution. It's amazing that this works. Okay, let's just randomly have a 1,024-bit number. And how hard is that to come up with? Pretty easy. Just flip 0, 1 times 0, 1 times 0, 1 times, and so on, 1,024 times. There is a random 1024-bit number. Okay, and then we'll just check. Oh, do we happen to guess a prime number? If we did, fantastic. That's our prime. If we didn't, try it again. So we need to check whether a 1024-bit number is prime, right? That's interesting, right? That's a hard algorithm. If you simply do something like, oh, I have a 1024-bit number, is it even? No. Is it divisible by 3? No. Is it divisible by 4? No. Is it divisible by 5? No. You're going to take a very long time, right? Is basically something on the order of 2 times 10 to the 24, right? Actually divide by 2 because eventually it's, yeah, but it's still a gigantic number. I mean, we're talking trillions. So let's not do that, okay? So how can we speed up with probability, okay? So there's a very famous algorithm that does this. Actually, there's several, but there's one that's really kind of the granddaddy of them all. And that is called the Miller-Rabin algorithm, okay? And the way that Miller-Rabin works is the input is a number x, and we're saying, is this prime? And so what it does is it takes advantage of a theorem from number theory called Fermat's-Little theorem. And that theorem tells us that if x is prime, and you look at a number k that's smaller than it, right? Then some combination of x and k, and I'm being vague because I don't want to get into the deep math of this. Some combination of x and k, let's imagine that is x raised to the k or something like that. Well, that actually happens to be equal to some specific value, let's just say it's 1, in modulo k, okay? It's not exactly right. I mean, the point is not important. What's really the point is that some operation that's fairly easy to compute should be equal to 1, okay? And if it is, great, right? Because the theorem guarantees that that's true for all k less than x. All right, so let's say that I do that computation, I ended up with a number of 5. Well, that's not equal to 1. And what that tells me is that absolutely, I mean, no doubt about it, x cannot be a prime. X has to be a composite, which is the opposite of prime. And that's simply because k failed the test, right? And we know that if x is prime, then every k will pass the test. Okay. Now, suppose that it fails the test. We know that x is not prime. Suppose it passes the test. What do we know? Well, this is kind of a conditional probability thing. And what we know, and this is not an easy result, but what we know is that x could be prime, probability of a half. Okay? A half, that's not very confident, right? And so you would hate to use Miller-Rabin for that. It's like, yeah, we think it's a prime, probability of a half. No, we wouldn't do that. The important thing is that k, it has to be true for all k, right? And different choices of k are independent. So let's say that I choose 2 values of k, right? k1 and k2. So k1 gives me a half probability that that it succeeds, right? Kind of badly, it's actually composite, but it does pass, so I think it could be prime. K2 again says, well, it could be prime. Probability of certainty from K1 is a half, from K2 is a half. These are independent, right? So the probability that we're making a mistake is a fourth. Okay, so if K1 and K2 pass the test, we're going to say it's prime, right? And the probability that it's prime is actually 3/4, right? Because the probability that it isn't prime, so I made a mistake, is a half times a half, 1/4. So 1 minus a fourth is 3/4. Now what if I do it 3 times? 1/2, 1/2, 1/2. Now the probability that I'm making a mistake is 1/8, right? So probability that I'm right if I say that it's prime is 7/8. Keep doing this. Pick 20 case. right? So let's say that one of them fails the test. Okay, it's composite. We're done, right? We were 100% right. All of them pass the test, right? The probability that one of them passes the test, and it shouldn't because the number x is prime, is a half. But they're independent. So the probability that they all say prime, even though x isn't prime, is 1/2 times a half times a half times a half, 20 times. 1 over 2 to the 20th. 1 over 2 to the 20th. 1 over 2 to the 10th is a million, right? So a million squared, right? So a million times 1,000 is a billion, times another 1,000 is a trillion. So 1 in a trillion chance that we're making a mistake. So the probability that x is prime is 1 minus 1 in a trillion. I'm willing to live with that, right? That's a pretty high probability. Oh, maybe you're not sure. Maybe you want more certainty. Okay, pick 40 case, right? So yeah, that's how Miller-Rabin works, and it's very, very effective. Well, that's only half the story, right? Remember what we said. We need to know what's the probability that a random number is prime, and then we have to keep checking random numbers until we find it. Okay, how many numbers do we have to pick? Okay. Well, like I said, there's two parts to the answer. The first part is just knowing if I pick a number at random, what's the chance that that number is prime? Okay, that's a hard question. That's one question. And the second question is, suppose I know that the probability is, let's just make something up, 1 out of 1,000. Then how many times am I going to have to pick numbers until I get one that is prime, right? That will tell me how long this algorithm takes. Okay, I pick k between 1 and n. What is the chance that it's prime? I'm going to give you an answer that's not very elucidating, okay? So the answer is pi of n divided by n, where pi of n is the number of primes up to n. Well, of course that's the right answer, right? What's the probability that k is prime? It's the number of primes divided by the total number, pi of n over n. So like I said, that's actually an accurate answer, a correct answer, but it just kind of begs the question, right? It's not very useful because it says, oh, what you really need to know is how many primes there are. Good luck with that, okay? Well, Gauss, our friend Gauss, kind of the mascot mathematician of this class, solved this problem, right? And it's something called the prime number theorem. And what it says that pi of n is roughly equal to n divided by log n, okay? So that is not true for small values of n. So for example, when n is equal to 10, there's actually 2, 3, 5, 7 primes, 4 primes, okay? That's not really n divided by log n, okay? Let's try 100. There are 25 primes, okay? Yeah, that's not quite right. But if you try something like 1,000,000 or 100,000,000, that's really accurate, okay? It's an amazing result, and you need a fair amount of number theory to be able to get that. Otherwise, you just kind of use it. This is something I know to be true. So yeah, pi of n is equal to n divided by log n. So what's the probability that a random k between 1 and n is prime? Well, that's the total number of prime numbers, n divided by log n, and then divided by the total number of numbers, which is n. So the n's cancel, and I'm left with 1 divided by log n. That's my probability, okay? So a 1024-bit number, log n, of course that depends on the base, but not by much. So log n is roughly equal to 1,000, okay? So we say that the probability is roughly equal to 1 over 1,000, 0.1%. Not great, right? But also not terribly frustrating, right? If I think I have a 1 out of 1,000 chance, I think I can find that with a computer, right? I may not want to do it by hand, but with a computer, 1,000 times is not that terrible. Okay. So suppose that the probability is p, like 1 out of 1,000. How many times do I have to try? Okay, that's the next question, right? Now that I know how rare primes are, or actually how common, I mean, it's just not that bad. How many times do I have to go back to the haystack until I actually get a needle, right? So that's an interesting question. And by the way, how many times do I have to go back? Isn't that an expected value kind of thing, right? I mean, it's a probability, right? So I want to have the average number of times that I think I might have to go in and grab. So let's do it with expected value. Okay, what I have here is 1. That's the number of trials, right? So what we're saying is, well, it could be 1. That could be the answer, right? And what is the chance that it's 1? Well, that's p, because that is success once, right? So I simply go out, pick something, I won, it was the right one. That was probability p by definition, okay? Now, I could also do 2, and again, this is the number of trials. And what I have is 1 minus p times p. So how can it happen that it takes me exactly 2 trials to get at this golden nugget? Okay, well, I must have failed once, because if I didn't fail the first time, right, then it would have taken 1 trial. So I must have failed the first time, and then I must have succeeded. Okay. Notice that the probability of failure is 1 minus p, right? Because the probability of success plus the probability of failure, these are these joint events, has to be equal to 1 because they're the only 2 possible events. Okay, now let's skip to 4 here. Again, this is the number of trials. And it took me 3 times. That means that I must have failed. I'm sorry, it took me 4 times. So I must have failed 3 times, right? And succeeded once. So if I take this sum, and it's an infinite sum, okay, but if I add all these numbers, I'll get the expected value of trials, because it's the sum of the trial times the probability that it takes that many trials. Okay, so let's try to find that sum, okay? And here it is. I'm using now kind of the standard sum notation. So I'll have the sum from I equals 1 to infinity of I, which is the number of trials, right? It could be 1, it could be 2, it could be 3, etc. And then 1 minus p to the I minus 1, that means the probability that I failed I minus 1 times. So fail, 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 and then the ith time I succeeded. So success once, right? So I fail I minus 1 times, I succeed 1 time, they took me I times to get a success, right? Now, I is the only variable here, so this is a variable, that is a variable, that there is just a constant, right? So I'm going to pull it out, okay? And I have p times the sum from I equals 1 to infinity of I times 1 minus p raised to the I minus 1. How do I find that sum? Okay. Well, that's one of the reasons why it's so important to be able to find the answers to sums, because these things come up in practice. And this specific sum you may remember because it's one of the ones that we did in the sections on series, right? So in particular, what we did was we figured out that the sum of I times x to the I minus 1 was 1 divided by 1 minus x quantity squared, okay? And this was true for any constant value x, right? So here's what we want. We want the sum from I equals 1 to infinity of I times something raised to the I minus 1. That's kind of our x, right? So using that same scheme, we get that that sum should be equal to 1 divided by 1 minus that x, which happens to be 1 minus p, the whole thing raised to the power 2. Okay, awesome, right? And of course, don't forget there's p in front. Okay, all right. So what is that? 1 minus 1 minus p, that's just p, right? So what I have is p times 1 over p squared, which is better known as 1 over p. Okay? This has kind of an attractive quality to it. Let's say that I'm flipping a coin. I got a 50% chance or a 0.5 chance of getting a heads, right? So how many times do you think I have to flip a coin before a head arrives? 2 would be a pretty good guess, wouldn't it? Right? You know, 1 divided by 1 over 2. Okay. What about rolling dice? I roll dice. How many times do I think I have to roll before I get a 5? 6 times? 1 divided by 1 over 6? Okay. So that's kind of the, I mean, that's an intuitive field that kind of convinces you that that's probably the right answer. This is a mathematical way of showing you that it really is the right answer. So for a 1024-bit number, right, I know that the probability of actually randomly hitting a prime is 1 over 1,000. So how many times am I going to have to try, okay, to get a prime? 1,000 times. That's not that bad. With a computer, 1,000 times, I'm not worried about that, right? And each time is pretty fast because Miller-Rabin is a fast algorithm, right? So yeah, I can actually come up with a random 1024-bit prime very quickly. And in fact, you can just go to your computers and, you know, generate public-private keys, and that's what's going on. And you can see that it doesn't take very long.